Today we're going to talk about our Riemann sums, our definite integral, as well as the trapezoid rule. This is unit 6.1. This is beginning our new semester, so all of this should be brand new information. So we're going to first begin with what we call equal with our Riemann. And so to do that, we have to kind of explore some graph problems. So what we're going to do is we're going to look at the graph of y equals the square root of 1 minus x squared. Hopefully, as you're watching this video, you're following along on a graphing calculator. If not, then you have access to calculators through my website. There's a graphing calculator on there, just click on it. So what we're going to do is we're going to plug in that. For the interval from 0 to 1, what we're going to use is RAM, which stands for rectangular approximation method, and the trapezoid rule with 5 rectangles of equal width. Before we get started, I'd like to write down some general rules, general formulas that we're going to use. Again, they're generic. That means we can use them as we need, and sometimes we may not always use them or the way that we see them. So our LRAM, again, this is if we are an equal width. Our LRAM is going to be equal to our delta x, which is actually going to be our height times every y value. So like, let's say we have y, that stands for y naught, which means the initial y value, plus y1 plus y2, and then we're just going to truck it all the way along until we get to, and normally we would write y to the nth, which means the last value, but we actually don't want the last value. We want the second to last value, so I'm going to say n minus 1, okay? And what all of these represent is this is base 1, base 2, base 3, all the way until second to last base. And I'll talk about what that means in just a second. But if we're looking at our RAM, then we have delta x, again that's our height, but instead of starting at the initial value, we're going to go ahead and start at the second value, or as some people like to say, they like to just start on the right hand side. So instead of the second to last value, we're actually going to start with y to the nth, the last value, plus all y to the, let's just say we got with 5, and then y to the 4th, all the way until we get to not the initial value, but y1, so that's that second to last value. Again, we can talk about this in a different way. We could have said delta x times y1 plus y2, all the way until we get to the last value. Either of these is acceptable. The other one we're going to talk about is our midpoint RAM. This is still going to be equal to delta x, and this right here is the hardest part about MidRim, is people want to change their delta x, but my delta x stays the same. So this is my note, hopefully you remember it, that my delta x won't change for my midram just because my midpoints are about to change. But so now, instead of using the initial point and the first point and the second point, what we're going to use is every half value point. Whatever that means on our intervals. So example, if y naught, if that initial x value associated with it was, instead of it being going, so we were saying 0, 1, 2, all the way until, let's say 5, from an interval from 0 to 5. Well, instead of 0 and 1, we would have 0.5, 1.5, 2.5, all the way until we hit 4.5. And so those are our 3 rectangular approximation methods. Well, what happens if we're approximating it using our trapezoid rule? Well, that's just going to be the formula of delta x over 2 times our first base, so y naught, plus 2 times all the middle values, whatever those are, all the way until we get to our last value. So the biggest thing to remember with our trapezoid rule is that our initial value and our last value are not multiplied by 2, but every value in between is. And I'll show you why. I'll give you that proof in just a second. Okay, but let's go ahead and move on with our actual question. So they're asking us to use both, so we're just going to explore this. So what we're going to do is first is graph our y equals the square root of 1 minus x squared. So there it is. But that's really zoomed out. So what we want to do is look at our interval from 0 to 1. So we're going to go ahead and zoom that in. I gave you your window settings here if you're using the TI Inspire to follow along. Otherwise, there it is, your zoomed in version. And what we're going to do is we're going to use our rectangular approximation method. And all this means is we are going to imagine that there are rectangles that we are creating, and we're going to take the area of each of those rectangles. Now I'm pretty short, so I'm not going to be able to quite reach, but if we imagine those rectangles, we can think here is, we'll say this is our y initial value, y1, y2, y3, oh, what am I saying? These are my x values, guys. My apologies. Ooh. So this would be my initial x value of 0 and 1. Sorry, not 1. These are my delta x values. So what that means is I have to figure out what these values are. So let's just say whatever they are. I'm going to bring my rectangle up. It's a terrible rectangle because I'm too short. And I bring it down, and boom, there's rectangle 1. And I come up from this value, and I hit that point, and I draw straight across, even though it's not going to cover my curve. That's okay. In fact, it's going to go outside my curve. Same here. I come up, go straight across, come down. I come up, go straight across, come down, up, straight across, come down. They're my terrible, terrible rectangles, but this you get the general idea. So before I talked about heights and bases. Well, all of these are going to be our heights. I know you're thinking, you're like, oh, don't we don't usually put height up here? But what I want you to do is I just want you to turn your head sideways and envision it this way. So this is actually going to be base 1. This is the base of this rectangle because this base has to match this, right? Technically. So we only need one line, right? Think about the area of a rectangle. I don't say, you know, height plus base plus base. Yeah, that's where it originated from. But really, we're actually just going to say base times height is going to be my area, and that's as simple as that. I think what I described as perimeter, actually, my apologies. But, so there's our base 1. This base, this line, is actually associated with this rectangle. This base is actually associated with this rectangle, base 4 with this rectangle, and base 5 with this rectangle. And I know what you're thinking. You're like, hey, what about this last section right here? Well, that's what we're going to talk about right now with our two traditional approximations, which is going to be our left and our right. But to do that, we need our y values, and we also needed our x values. We did get that those x values are pretty easy. It told us we had an interval from 0 to 1, and they wanted 5 equal, that's what they gave us in the formula. They said 5 rectangles or regions or whatever they called it. So all we do, the formula for delta x, which is where these numbers came from, the formula for delta x is simply b minus a over n. And so here's my b, here's my a, divided by n is the number of regions we're going to use. So that's very simple. 1 over 5, 1/5 is 0.2. So all of my values will be 0.2 between these. So from 0 plus 0.2 is 0.2, plus 0.2 is 0.4, plus 0.2, etc., all the way to 1. And yes, we have 6 values, but it's going to create 5 regions. 3, 4, and 5. So there are my 5 regions. Okay, you fill this out using your calculator very simply. I gave you a hint with the TI Inspire. If your equation is already in the graph, then you can go to menu, hit number 5, and hit number 1, and that's going to get you to graph trace. And all you do is enter in this value. So I hit 0, and I enter in 0, and I hit enter, and it gives me my y value. I put 0.2 and hit enter, and it should give me my y values. But I already have that in here, so we can see at 0 it's going to be 1 when x equals 0.2, when x equals 0.4, when x equals 0.6, 0.8, and 0.1. So there are our y values we now have. So we're going to go ahead and approximate it using our left endpoint, which is what I demonstrated in that my horrible rectangles. So here we go. Whew, I went too far. Here we go. Here's our left rim. So our left rim is going to be equal to the area of each rectangle. So area plus area plus area plus area plus area. And I told you guys before that we call this delta x actually our height. So the distance, the change between my two x's, which is what delta means, change in x, the distance between those two x's is going to be the height. And do they repeat? Yeah, the distance is still 0.2, 0.2, 0.2, 0.2. Algebraically, what can we do? We can factor out that 0.2. So that's where that formula comes from, delta x times all of my base values, my y values, and so that's where they come from. So because we're doing the left, we're going to start with the initial value and go all the way until second to last. So here's our last value, here's our second to last value. once I plug in those numbers, which we got using our table, once I plug in those numbers, we actually get our true approximation. And this should have said, my apologies, it should have said approximately, but that's okay. So 0.85926. Okay, so moving forward, let's actually work through our right RAM. So the only real difference between our left and our right is that we're actually going to be using the right endpoint. There's another typo on the screen, sorry. The right endpoint of each subinterval. So we can draw it one of two ways. We can start right here. Well, this endpoint interval means that I'm at the very bottom. That's where the curve hits. So I'm not really creating a rectangle. But over here, I can hit my curve, draw straight across, hit my curves, draw straight across, hit my curve, draw straight across, and then the final one. So previously, we saw our left rectangles went a little bit over, and our right rectangles are going to go a little bit under. That's for this example. We'll talk about what that means in just a second. So what we're going to do is we're going to go ahead with our right. So again, our delta x, which was 0.2, that's going to be on the outside, so 0.2, times all of those y values. So with our right, we start with the rightmost value. So right, and then all the way until second to last. So I'm going to go all the way to 0.2, so from 1 to 0.2. And there we have it, 0.2, y1, 8, 6, 0.7, 0.4, and 0.2. I plug in those true values, and I get my actual approximation, which is approximately 0.65926. Okay? Now we're going to go ahead and finish this up. We're going to skip, I know we talked about the midpoint, but we're going to skip that for just a second. We're going to move to the trapezoid rule. Okay, so here's where our trapezoid rule comes from. If you've forgotten the formula for area of a trapezoid, it's just 1/2 times the quantity base 1 plus base 2 times height, which is this right here, this formula right here. And so when we extrapolate that out into our separate trapezoid areas, that's where our trapezoid rule comes from. So here are those values again, and we're just going to plug it in. So first, let's see what these look like. What do I mean by here are my trapezoids? So we have our trapezoids right here. Again, this is my height, so I want you to turn your head sideways, you know? We're actually doing, that's a funky looking one right there. Okay, so we're actually doing our trapezoid sideways. So this is still our height, but this is going to be our base, our bases. Okay, so again, the area of a trapezoid is usually base 1 plus base 2 times height all over 2. Okay, we know our heights. Our heights are always going to be the same because it's equal width. And our over 2 is always going to be the same. So we pull that out, we factor it out, and that's where we get that delta x over 2 on the outside. And then we're going to multiply by our bases. So the first base we're going to have is this one right here, base 0, and then base 1, and then base 2, base 3, base 4, base 5, etc. But remember, with trapezoids, we use multiple bases. So if you were curious earlier about where that 2 came from, here's my proof. So we have that delta x over 2 right here, or 1/2 times delta x, however you want to see that. And then what we're going to do is look at each individual trapezoid. So here's trapezoid 1. This is base 1 and base 2. So 1 plus 0.9798. Okay? Here's trapezoid 2. Here's base 2, base 3, or whatever numbers I gave him. I can't remember. So here are those values. Here are those values for trapezoid 3, trapezoid 4, and trapezoid 5. Well, what happens? Let's look at that. Okay, 1, do I see 1 anywhere else? No. But do I see these numbers? Did they repeat? Yes. Did these numbers repeat? Yes. Did these numbers repeat? Yes. And did these numbers repeat? Yes. But did my last number repeat? No. Well, why? Well, if you think about your trapezoids, this one shares no base with anybody. There's nobody to the left. But these share a base, these share a base, these share a base, these share a base, and finally, there is no shared base on this. So again, we can extrapolate mathematically that it's 2 times, 2 times, 2 times, and that's where that formula comes from. So we say 1 plus 2 times base 2 plus 2 times base 3 plus 2 times base 4 plus 2 times base 5, all the way until we get to our last value where we don't multiply by 2 either. So we plug it in, we get approximately 0.75926. And then going back to our MidRim, and the reason why I skipped this till the end is because with our MidRim, you actually need new y values. So I wanted to make sure we addressed our trapezoid rule, which needed the same y values before. So what we're going to do is we're actually going to approximate this at the midpoint of each subinterval. So instead of 0 and 1, we're actually going to be looking right here, and right here, and right here, and right here, and right here. And so if I draw that rectangle, it kind of comes like this, and I hit this point, go out and out, and it comes like this, hit this point, go out, etc., etc. So I'm connecting where my midpoint would have hit, and I'm drawing a rectangle around it. Okay, so what we're going to do is first we need new y values, so I'm going to put those up there for you. There are our new y values. How did I get my new x values to get my new y values? Well, that's pretty easy. This originally was 0, and this originally was 0.2. What is the distance between here, 0.2? What's 0.2 divided by 2? 0.1. We got lucky because we're starting at 0, so 0.1. And then from here, you can kind of make a decision how you want to see this. Most of us can see this pattern form, but 0.1, you can either add delta x, which was 0.2 in our instance, so 0.3, or I can look what's between 0.2 and 0.4. Well, that's pretty easy, 0.3, and then 0.5, and then 0.7, and 0.9. That's where those values came from. Pretty easy, right? So here is our midpoint Riemann estimation. Again, here's where I'm going to talk about my delta x is still the same. A lot of people, when they see this midpoint, they want to divide their delta x. They're like, oh, okay, because it's a midpoint, my delta x is no longer 0.2, it's 0.1. But that's not the case, because what's the distance between each delta x still? 0.1 to 0.3 is still 0.2. 0.3 to 0.5 is still 0.2. Okay, so common mistake, let's not make it. All right, so then I'm going to use every single one of my midpoint values. Because it's not a left nor a right, it's actually the midpoint. We're actually going to use all of them. I should have the same number of midpoint x values as I have for regions. So we're looking for 5 regions. I've got 5 values, so we're good. Plug it in, and boom, we get the answer approximately 0.79299. Okay. And then I'm going to ask you some questions. So we talked about earlier, I mentioned, there was that some of the rectangles went over and some of them went under. And so what does that mean? Was my left, the very first one we did, was my left Riemann an over or under approximation? Think about where those rectangles were. Were they over or under the actual curve? Well, they were actually over, weren't they? So they were an over approximation. Why though? You can't just tell me, oh, it's my rectangles over the curve. No, it's because the graph of y is actually decreasing. You have to think about it that way. If we have some curve, my graph of y, if it's decreasing, then my left values are always going to be an over approximation. If it's increasing, then my left values are going to be an under approximation, et cetera, et cetera. So it's easy to kind of think of it that way. And then our next question was our right ram going to be an over or under approximation? In this instance, it was an under approximation, and this is because the graph of y is decreasing.